Alright, welcome back. We're gonna take a look at composition of trig functions, and this time we're gonna look at compositions that end up being expressions and not actually values. So what do I mean by that? Well, let's look at this example again that we looked at in the last video. It looks almost identical, except you'll notice if you compare it to before that we were evaluating a composition at a particular value, and so our answer was a value. This time we're taking the composition of a function, and the answer is not going to be a value, it's going to be an expression. So let's just quickly review how we do this with normal functions, or functions that aren't trig functions, I should say. So f of x we know is 3 times the square root of x plus 7. And so as we work our way from the inside out, we make some substitutions. So if f of x is 3 times the square root of x plus 7, then I'll put that in place of f of x. And now I'm doing g of this whole thing. So in the function representing g, wherever I see an x, I can replace it with 3 times the square root of x plus 7. And so the big idea is that we're not doing anything different, but notice our answer is actually another function or expression. It's not a numerical value. And so keep that in mind as we look at these trig compositions. So we have tan of cosine inverse of x. And it's very important to identify what that x represents. So if I'm taking the inverse cosine of x, the question is x an angle or a ratio? Well, think about it. If you go off to the side, and we usually do things like cosine of 30 degrees, right? And we get answers like root 3 over 2. The input was an angle, and the output is a ratio. So that when you do cosine inverse, your input has to be a ratio, and your output is the angle. So what that means is this in the parentheses must be a ratio. Now it doesn't look like a ratio because it's just the variable x. To make it look like 1, we're just going to write it as x over 1. Okay, and now the rules of the game are still the same as they've always been. We start with the inside piece. And so we're going to go over here, and the only difference now is that I don't know, x is just an expression. So before, in the other problems, right, I would use my restricted quadrants for cosine inverse, and I would draw my triangle in the quadrant that was appropriate depending on the sign of that ratio. But this is just an expression, so we don't know if it's positive or negative. So I'm going to do the restricted quadrants, but I'm just going to draw the triangle in the first quadrant, because I mean x, who knows, it could be positive, it could be negative, we're not sure. So we'll just draw it in the first quadrant. Notice that our output, by the way, is going to be an angle. So now I have to fill out the sides of this triangle so that the cosine of the reference angle is x over 1. And so by definition of cosine, the x would have to go here, the 1 would go here. And the answer to this question is, what is that angle? Now here's the thing, we're never going to know what that angle is because this is just an expression, right? We can't solve for x in this problem. But we're going to, so that angle is just, we're going to call it theta. So we're going to be taking the tangent now of that angle theta. So what is the tangent of this angle? Well, the tangent is opposite over adjacent. The thing is, we don't have an expression for the opposite side now. But we can come up with one because this is a right triangle, and we know the Pythagorean theorem. So let's just call that side A for now. And according to the Pythagorean theorem, a squared plus x squared equals 1 squared, which means that x squared, which means that 1 minus x squared is equal to a squared. And if I square root both sides, and get square root of 1 minus x squared. I did not have to do the plus or minus square root because this is a distance, a length, that we're viewing as a positive, and lengths of triangles we're viewing as positive. So now that I have that opposite side, I can actually evaluate this. Tangent of theta is square root of 1 minus x squared divided by x. So notice we did all that without ever knowing what that angle was. We didn't really need to know what it was. I'm going to do another example here a little more quickly. So as usual, we start from the inside. That is a ratio, and so our output is going to be an angle. And then we're going to take the secant of that angle. So again, we can put in the restricted quadrants for sine inverse. And we're going to draw our triangle in the first quadrant simply because x is, we don't really know what that ratio is, so we'll just use the first quadrant. So I fill out the sides of this triangle so that the sine is 3 over x, which means that's a 3 and that's an x. And the answer is that angle theta. So now I'm taking the secant of that angle. And if you notice, the secant of that angle, which is the reciprocal of cosine, that requires that I know this side right here. So I have to come up with that as an expression. So again, the Pythagorean theorem is what we're going to use. So a squared plus 3 squared equals x squared, which means a squared equals x squared minus 9, or a equals the square root of x squared minus 9. And so now I have the information I need. The secant of this angle, by definition, is the reciprocal of cosine, so it would be x over square root of x squared minus 9. As one final problem, we're going to take a look at this one. The process is similar. You'll notice that this time we don't have a variable as a ratio, or in the ratio, but we still approach these problems the same way. So I'm going to go over here and I'm going to draw the restricted quadrants for sine, and that's a positive ratio, so I'm going to set up my triangle appropriately, and that angle here is what sine inverse of 4/9 is going to be. So now I'm taking the cosine of that angle. So you might think you got to go to your calculator now to evaluate, for instance, the inverse sine of 4/9 to find out what that angle is, but the point is we don't have to use our calculator to get the answer to this question. So you can expect this to be on like a non-calculator type problem on the test. I need the cosine of this angle, and once again I need to know that adjacent side. So the Pythagorean theorem is going to get me that side. So now a squared plus 16 equals 81, and so a squared equals 81 minus 16 is 71 minus 6 is 65. Yep. So a is the square root of 65. And so this is square root of 65 over 9. At no point do we need our calculator. Alright, so I hope those are 3, I think, good examples that you can use to evaluate trig expressions.